Now we will start with the Debargha.
Okay, it's a good evening, everyone. It's a pleasure to have Professor Freddy Saia from University of Illinois, and he is going to speak on CM points and external. Over to Freddy, please.
All right. Thank you very much. Thank you for the invitation. Happy to speak here. I haven't been able to attend the prior talks in this trimester synchronously, but I have been keeping up with the recordings and slides posted. Some really great talks. And I'll reference some of the kind of arithmetic, algebraic, analytic gadgets that other folks have talked about in this talk. But mainly this is meant to be a gentle introduction to CM points and Heegner points with something of a view towards the applications of interest to folks in this seminar, at least to my knowledge. So we'll talk about, of course, like basic definitions and like different vantages on CM points and Heegner points. And then I'll end the talk by giving just like a slight historical background and motivation for like why we're looking at Heegner points and just a statement of Zagier, and maybe I'll mention like some generalizations that I think are of interest to the folks in the seminar going forward. But that'll be it. But along the way, I'll also just to kind of shoehorn some of my own work into here, talk about more recent perspective on CM points and I guess Heegner points in particular, if you want. That's kind of computationally helpful, perhaps not for things like getting coordinates or working with explicit models, like for application towards things like Zagier, but for counting CM points, determining residue fields, things of this nature, that'll be work of myself and Pete Clark, my PhD advisor. So okay, that's kind of the idea of this talk. Let's head into it. I know it's in the evening for you all here, so thanks for accommodating. I hope you're not too tired and we can kind of have something of a exciting talk. Feel free to interrupt at any point in the chat or just like unmute and feel free to shout out at me if you have questions or comments throughout. Let me make this so I can, I'll just slide, I suppose. So to start out, if we're going to talk about CM points, I need to talk about modular curves. So people always say that mathematicians don't really mind being told things they already know. In fact, a lot of people like it. So I assume a lot of the beginnings here will be things that the experts already know, but okay, here it is. If we have a Fuchsian group, so some finite index subgroup of the full modular group, I'm calling gamma of 1, just SL2Z, we attach a modular curve to it. So I'm just working over C right now. I'm putting maybe more decoration than's necessary here with this, like, also it's over C, just to remind you this is my model over C, because we'll have algebraic models in a second. So okay, ignore that if you want. I'm just saying that I have an algebraic curve whose points are the upper half plane modulo this Fuchsian group gamma. So H here is my upper half plane. And the action of gamma on H is the usual one by linear fractional transformation. So if you have an element of SL2Z, a matrix like this, you act on an element of the upper half plane Z in this fashion. And so this gives us a curve Y gamma over C. And you can compactify by adding finitely many cuspidal points to get a compact curve X gamma over C. So this is a Riemann surface. You can ask about its genus, etc. And equivalently, you can do this by kind of compactifying the upper half plane, taking the extended upper half plane and quotienting by your same Fuchsian group gamma. So these are our curves over C. In particular, we have the J line. So if you take the full modular group, all of SL2Z, you get kind of your bottom curve that you expect. So this is just isomorphic to the projective line over C if you compactify. So that's our X of 1 here, I'm calling it. And classically, we know that this thing, it's non-cuspidal point, so Y1 of C, parameterizes elliptic curves up to geometric isomorphism. So elliptic curves over the complex numbers up to isomorphism, or equivalently lattices up to scaling, right? An elliptic curve is has a corresponding lattice. You realize it as C modulo the lattice. And okay, this is the full modular group. So this is kind of our bottom modular curve. If you take any Fuchsian group, you get a natural quotient map from that modular curve to the J line. And both of these have natural quotient maps from the upper half plane, just from their definition. Okay, so these natural quotient maps will come into play when we talk about CM points, when we give the definition. And our main interest in this talk is going to be this classical family of modular curves. So x not of n. So n is an integer here, a positive integer. This is a family of algebraic curves actually with models over Q. So when I write x not of n instead of with the over C decoration, I mean the canonical model over the rational numbers. And as we just said, we have a natural map to the J line. This is in fact an isomorphism when n is equal to 1. So x not of 1 is just another name for the J line. And it's of this degree psi of n when n is at least 2. So this is just the Dedekind psi function. So it's the multiplicative function, which at a prime p, psi of p is p plus 1. So it's like the Euler phi function, except it's p plus 1 instead of p minus 1. When n is at least 2. We said it's an isomorphism when n is 1. And what do I mean by like they have models over Q? I just mean if you base change this curve from spec Q to spec C, you get these complex, the associated complex modular curve that we talked about before. This is the one associated to this Fuchsian group. So gamma not of n, this is just matrices in SL2Z, which are upper triangular modulo n. So this entry C is divisible by n. So this is going to be the family of modular curves we're interested in this talk, mainly because of their specific moduli interpretation. So in general, modular curves parameterize, you should think elliptic curves plus some extra level structure, so some extra torsion structure. And in particular, these curves are parameterizing elliptic curves with a cyclic order n subgroup of its n torsion. So by F rational here, I just mean that cyclic order n subgroup is fixed by Galois. It's Galois stable. And when I say Galois, I mean F rational. I mean the absolute Galois group of F fixes C. Or equivalently, this is going to be kind of more the advantage in this talk. It's parameterizing cyclic n-isogenies of elliptic curves over, whatever number field, say F, you want to put here. These things are equivalent, of course, because, okay, if you have an n-isogeny, you take its kernel, that gives you, by definition, a cyclic order n subgroup. If you have a cyclic order n subgroup, there's a natural quotient of E, so we call it E modulo C. And you have an isogeny from E to E mod C, just that natural quotient map. And I want to be careful, these are coarse moduli spaces, so that's why I've put isomorphisms over C everywhere here, rather than over Q or over F. Right, so these modular curves are parameterizing isogenies of elliptic curves. We are interested in that exact torsion data. And so we want to talk about CM points. What is a CM point? I'm going to give you, I don't know, 3 sort of vantages at the very least. So here's one which maybe I've stated somewhat complicated here. I think the next slide, I'll give you the moduli interpretation, which I think will, I don't know, in my opinion, it's more down to earth. I'm more algebraically minded. This is maybe somewhat analytically minded. But we're going to have throughout this talk, capital K is always going to denote an imaginary quadratic field. And to define a CM point, I'm going to specify an embedding of K into 2x2 matrices over Q, this split quaternion algebra over Q, if you will. So I'm just like fixing, like suppose I'm handed a specific embedding, I care about the choice. And we're going to assume that this embedding optimally embeds an order O into M2Q. So I'm just fixing O to be an order in K, the order in K that's optimally embedded by this embedding. And by that, I mean this condition is satisfied. So what is this saying? This is saying, well, you embed capital K into M2Q, you intersect with this maximal order, this maximal quaternion order in M2Q, and then you pull back and see what you get, and that'll be an order in the imaginary quadratic field K. So when I say order in K, I mean it's a subring, which is a full rank Z module, Z submodule of K. So this could be the full ring of integers of K, or it could be some non-maximal order. Either is fine for me. So with all this set up, there's a unique element of the upper half plane which is fixed by the image of this order under this embedding. And we call that a CM point. And when I say it's fixed by this image, I mean under this action by linear fractional transformations, right? We're getting elements of this image are in M2Q, and so they act on the upper half plane in the way we spelt out before. Okay, so we call Z a CM point. And then we have all these natural quotient maps to modular curves, something I'm calling X, and we call the image under any such map onto some modular curve X of Z a CM point, or a KCM point if you want to be particular, or an OCM point if you want to be very particular. Okay, but I'm thinking about elliptic curves. I hope you are too, unless you're very complex analytically minded, that's also okay. So what does this mean on the moduli side? Well, it means what you would think when you hear complex multiplication. So if you look at the geometric endomorphism ring of an elliptic curve, let's say it's over a number field F, there's two options for it over a number in characteristic 0. So it's usually just the integers. So this is the ordinary case. So you have multiplication by n maps for every n. Your elliptic curve is an abelian variety. It has a group. It's K rational point or F rational points has a group structure. If it's any bigger, it has to be an order in an imaginary quadratic field, let's say K. That's what we're calling it. So a thing like what we saw on the previous slide, which we're calling like little o throughout this talk. So again, it could be the full ring of integers, which I'm calling OK here, but it could be a finite index submodule of that. And then this is the case of complex multiplication when you have more than just the usual endomorphisms on your curve. And if we want to be very specific, we'll say CM by this order O when the geometric endomorphism ring is O. And okay, so that's what it means for an elliptic curve to have CM. What does it mean for a point on a modular curve to have CM? Well, it's what you think. It's induced by an elliptic curve with CM. So on the J line, that's exactly what it means, because a point on the J line X of 1 is just the data of a geometric isomorphism class of an elliptic curve. So a class of some E like this. We call that point an OCM point. And then the notion of being OCM is preserved along fibers, or at least the fibers of these natural quotient maps between modular curves. So if you take any other modular curve, a point on it has OCM if its image on the J line has OCM. So equivalently, it has OCM if it's induced by an elliptic curve with OCM plus extra level structure. But I like this vantage of thinking about it as a property that's preserved along fibers, because then you start thinking about, well, the OCM loci on these curves, kind of the collection of closed points with CM by a specified order. And you're just very concretely saying, well, that is just the pre-image of some closed point on the J line. The points in the pre-image of a point on the J line. And so we'll be talking about CM a lot, so I just want to give you some reminders about kind of arithmetic and imaginary quadratic orders, or quadratic fields. So an imaginary quadratic order is determined up to isomorphism by its discriminant. Or if you prefer, if you want to fix your K from the outset, like we'll often do in this talk, so you fix an imaginary quadratic field K, then an order in K is determined up to isomorphism by its conductor. So this is just this index of O in the full ring of integers OK. And here's your relation between discriminant and conductors, right? The discriminant of your order is your conductor squared times the discriminant of your maximal order. So we'll use either of these data throughout the talk to refer to a CM order. And if we fix an order, O, the one, say, of discriminant delta, we'll write J of O or J of delta for the J invariant of an elliptic curve with CM by that order.
Sorry to interrupt you. So you have a definition of the CM points. Is it you have this map pi? Is it the image of I and rho under the map pi is the CM point? So it can be something more than that.
It can be something more than that. So your CM points don't have to have non-trivial stabilizer.
Okay. So is there what are the examples? You have this I and rho. I mean, is there any other points?
Yeah, you can have, so I and rho are points with CM by discriminants -3 and -4.
Yeah, that's right. Okay.
You
can be something.
Yeah, so on your J line, or I guess on any modular curve, you have CM points by any discriminant. So take any discriminant you like, you have CM points by that discriminant. I'll give you, I'm not gonna at any point in this talk give you like coordinates over the complex numbers, but I'll give you another vantage that I think is like kind of combinatorially satisfying. Like this is how I now think about CM points. And I'll talk about some like I think -15 CM points maybe.
Okay. Thank you.
Yeah, no problem. Yeah, at any point, feel free to shout out. Please do ask questions. And so on this J line on Y of 1, I'm not caring about the cuspidal point. There's a single closed point of degree, the class number of your order, with residue field isomorphic to Q adjoin the J invariant. So it's like the minimal field of definition of an elliptic curve with CM by O, which is induced by OCM elliptic curve. So if like kind of related to that question, fix any order you like, fix any discriminant you like, imaginary quadratic discriminant. So by that, these are just negative integers, which are 0 or 1 mod 4. Those are your discriminants. Then there is a single closed point. So a single algebraic point over Q on this curve Y of 1. That is the kind of the OCM closed point on the J line. Of course, that could have several geometric points. Like when it's -3 or -4, these are class number 1. So you have a single geometric point. So the class number here is 1. But you can have imaginary quadratic fields of arbitrarily big class number. But they're all, those geometric points are giving you a single closed point on Y of 1. And then to get points on general modular curve, you're just taking fibers over the natural modular maps. And this is all given to you by the main theorem of complex multiplication. So that tells you a bit more than I'm saying on this slide. It tells you kind of how these Galois groups act on CM points in a very, very explicit manner. So Chamorro reciprocity, if you want to say those words. But here I'm just telling you kind of what I said on the last slide. So the main theorem of complex multiplication tells you that we have explicit class field theory for imaginary quadratic fields, kind of like Kronecker-Weber gives you for cyclotomic fields. So if you fix an order and you let K of O, so K parentheses O, I'm letting denote the ring class field corresponding to O. So that's just the class field associated to this Galois group. So the Galois group of it over K, so it's an abelian extension of K with this specified Galois group, the class group of your order, which has size, the class number of your order. Then if you take K, your CM field, and adjoin the J invariant, of an elliptic curve with OCM, you get this class field. So these singular moduli, the J invariants of CM curves, generate these ring class fields. That's part of what the main theorem of complex multiplication tells you. So these are, at least over K, these are going to be the residue fields of points on the J line. Over Q, it's going to be Q adjoin the J invariant. You might call that like a rational ring class field, but I don't know if that's entirely in vogue. But okay. So we're talking about CM points now, but let's remind ourselves of the moduli interpretation for these curves we're interested in. So y naught of n is parametrizing isogenies, right? And so just to give you kind of a more obvious containment of residue fields on this slide, well, I just said the point on the J line has residue field over Q. Well, Q adjoin the J invariant, or Q adjoin the J invariant of E2 for if you look at the points on the J line corresponding to E1 or E2 separately. By that, I'm just saying the minimal field of definition of E1 is this field, and the minimal field of definition of E2 is this field. And so if you want your isogeny to be defined, i.e. if you look at the residue field of the corresponding point x to this isogeny on y naught of n, then both E1 and E2 must be rationally defined over this residue field. So you get that both Q adjoin J of E1 and Q adjoin J of E2 are contained in the residue field of this point. In particular, their compositum therefore is. And then you might ask, like, okay, well, is this an equality? Is it any bigger? And the answer is basically, well, it could be as big as take this, but composite it with your CM field K. It's somewhere in between those two things, like this, and then the same thing, but replace the Q's by K's. But it always looks like a field of this type, like a ring class field or a rational ring class field. So Q adjoin a J invariant or K adjoin a J invariant. And that's what I'm saying on this slide. So I think at least part of what I just said has certainly been known. But I'm stating this as a theorem of Pete Clark and of Pete Clark and myself. The latter work is handling those two CM discriminants that were mentioned in the question. So they turn out to be especially pesky ones because of the fact that they have extra units. So this is saying you take any KCM point, let's say it's by discriminant delta, then the residue field over Q of this point on x naught of n is either Q adjoin a J invariant or K adjoin a J invariant, where the J invariant might not be of a curve with discriminant delta, but it's of discriminant m times delta for some integer m between 1 and n. There's some divisor of n, where n is just the level of your modular curve. And here is like the part that is certainly new in this theorem. Moreover, there exists an algorithm to provide a count of all closed delta CM points on this curve with each residue field. So like with if you range over all the possible residue fields that could occur, so all the divisors m of n, we can tell you the count of closed delta CM points on x naught of n with that residue field. And this is like an implemented algorithm. You can find it on my GitHub. And in fact, a slight more of a plug, if you care about Shimura curves, which I do, if you want to let capital D be an arbitrary, indefinite quaternion discriminant of a quaternion algebra over Q, you can generalize this to general quaternion discriminant. At least, sorry, I should say coprime to the level n in this slide somewhere. So the D equals 1 case is just recovering the elliptic modular curve case. So in red, I've appended those to the Clark and Clark-Saia results. And then it's work of myself that you can extend this to D larger than 1 through similar methods. So I'll tell you a little bit about those methods now, mostly because I want to give you this extra vantage on CM points that it affords. And this is the vantage of isogeny volcanoes. So what do we do in this work? We provide, in some ways, a combinatorial perspective on CM points. When I say algebraic points, I should say CM points here, which is useful for getting an algorithm of the sort I mentioned on the previous slide. So we're going to fix a prime L, just a rational prime, and GL is going to be this isogeny graph. So its vertices are going to be in correspondence with isomorphism classes of elliptic curves with CM. CM by any discriminant. You can the discriminant can vary. Those will just vary over different connected components of this graph. This graph won't be connected. Edges between two vertices will correspond to classes of cyclic L isogenies between the corresponding elliptic curves, right? So each of these elliptic curves corresponds to a vertex. This is an edge between those two vertices in the graph. And this seems to give a directed graph because an isogeny has direction. But okay, I'm sweeping a little bit under the rug, but usually we can ignore direction of isogenies because each isogeny has a dual isogeny in the opposite direction, and we can just identify those directed edges and think of undirected edges. And so here's kind of the main theorem that tells us that at prime power level, paths in these graphs correspond to points on these modular curves. So that'll be the second result here. First off, I'm saying that we have this correspondence between cyclic prime power isogenies of elliptic curves with CM and certain non-backtracking paths in these graphs. Sorry, this capital D should go away here. That was a holdover from the Shimura curve case. We're just thinking about elliptic curves here. So this is kind of just coming from the definition of the graph, right? Edges are cyclic L isogenies. If you take paths, you're getting L power isogenies. The non-backtracking is just to make sure they're actually cyclic. Like you don't want to get a non-cyclic isogeny by traversing an edge and then following it up by its dual and getting like a multiplication by L map. The interesting thing is, well, you take this and then you add a Galois action because you want to think about points on your modular curves. So you can define a meaningful, in terms of the moduli interpretation, action of the absolute Galois group of Q on these graphs and paths in them by just acting on the corresponding isogenies, right? These are algebraic objects. You act on coordinate or coefficients. And if you quotient by this action, you get exactly CM points on Y naught of N, right? Galois equivalence classes of cyclic prime L to the A isogenies. Where here, sorry, I should have N should be a prime power. It should be L to the A. So this is all for prime powers. How do you do it for general level? Well, we have a theorem that tells you that you can kind of compile information across prime powers algebraically. The thing you do is you take fiber products of your CM loci, essentially, and which corresponds to taking kind of composite of residue fields. So you really can go to general level, not just prime power level, using these volcanoes. And here's an example. So I'm not telling you what the definition of an L volcano is. But they look like this, and I just want to tell you that it's a.
Sorry, can you
very-
just tell that what is this L volcano means like quantifies?
So all I want to get across in this talk is that an L volcano is a very specific graph theoretic structure, and it's super amenable to computation. So it's super simple. I'll point out some of the salient features on the next slide.
So you
But
want to understand some properties of the CM points, right? And then, I mean, if you have two different L volcanoes, then it will tell you something else. It's like these are two different, right?
so you fix your discriminant and
Okay.
you fix your prime power, and you want to understand CM points by that discriminant on this modular curve, and you can kind of quantify CM points with specified residue field on this side by quantifying paths with specified fixed field on this side. So we work to explicitly understand the action
So
of
there is one
Galois.
GLD and there is one GL. So GLD is a corresponding Shimura curve, right?
Yeah, sorry. The D should go away. We're just thinking about modular curves, but you
Okay, so
can
there
do
is no
this all
D
for
there, right?
Shimura curves. There should be no D here. That's a holdover on my part.
Okay.
That can be
So
ignored.
there is a Galois group action there on this part, and what you were saying, this L volcano. So you have this, you have all this L power n torsion, L power n plus one torsion, and all these torsions are there. And these volcanoes will give you information on that.
Yeah, so let me show you an example. So here I'm fixing my discriminant to be -15.
Okay, cool.
So this is a certain class number 2 discriminant, and my prime, I'm just choosing my prime to be 3.
Mm-hmm.
And so here is part of the corresponding volcano. So it will continue going downwards, but I've capped it off at level 2. Um, so you have levels, right? So here is my level 0, the 2 vertices at the top. Level 1 is the 6 vertices down here, and then you should have
So
18
how does
vertices
this
down here.
Galois group acts on this graph? Is there action of the Galois group on this graph?
Yeah, so each of these edges, so these 2 vertices at the top, for instance, these are corresponding to the 2 isomorphism classes over C of elliptic curves with -15 cm.
Okay.
There is an isogeny between these two. This edge is corresponding to that. And Galois acts on isogenies.
Mm-hmm.
And so you transport that structure, you transport that action to paths in these graphs. And okay, what does explicitly understanding the Galois action mean? Well, we know from the main theorem of complex multiplication basically everything. We know that first of all, if you fix a discriminant, if you fix an order, all of the CM points by that order on the J line are Galois conjugate. They're acted on transitively by
Sure.
the Picard group. And then
So this graph is up to Galois conjugate or no?
this one is not yet. No, this is just isomorphism classes over C. The
Okay.
thing that you really need to understand from there is how complex conjugation acts on this graph. And I haven't decorated this graph to add that, but in our work we do. So you add decorations to see with like kind of quantify how many paths can be fixed by complex conjugation using various combinatorial methods. It gets slightly complicated, but not too complicated that we can't do it. And so you use that to enumerate closed points on your modular curve.
So this like is there any okay? This looks okay. It may be very loose comments, but is there any connection with Decidian-4? So whatever you're drawing,
With this and what?
this graph you are drawing, is
Mhm.
there any because there's only one color, right? But is there any connection with Decidian-4? Design. Is there any connection with design?
With the sign?
Design,
Actually, the
design.
form, the Grothendieck he's
Authentic
talking
Decidian.
about.
Oh, with the other slide. Um, so I haven't added in coloring to like kind of indicate the action of complex conjugation on this volcano. That's the sort of thing you do. On this slide, I'm just wanting to give you the structure of the volcano. So I wanted to point out some salient features. So the in
So
particular, as I've
there is a connection, right? That's what you were saying. Design,
uh,
index design, the way that we have drawn the graph. I can see there is only one color. So is there any connection to that? Okay. So this graph, can you show to the previous slide? I mean, where you have vertices
mhm.
and yeah. Not okay. This is up to conjugate, but the vertices and edges. Can you show how we were just putting these vertices and edges?
Yeah, so this is really the correspondence that I'm meaning to. I mean, okay, I'm looking at this side of the correspondence on the next slide. So, like, for example, this edge here is corresponding to a 3 isogeny, as is every other edge in this graph. So, for
Sure.
example, if you start at this vertex corresponding to a CM point by in this, field with conductor 3, You can follow this edge up by this edge and get a 9 isogeny between these two vertices. You can take another edge to get a 27 isogeny. And you can think about how Galois is acting on that path. So that path will induce a point on your modular curve. And then you want to understand, well, what is the residue field of that point? And what is the orbit of that point under the action of that path under the action of Galois, i.e. the corresponding point on the modular curve under the action of Galois?
Thank you.
Yeah.
Thank you. Yeah, thank you. Okay, that's good.
So yeah, the structure of this graph is, at least of the surface of this graph, these vertices at level 0 at the top of the graph in the way that I'm drawing it, they're determined by the splitting behavior of L, your prime, in your field K. So this is the ramified case. L is ramified in this field. You get a single edge coming out of each surface vertex if you think of the surface as a subgraph. If you think about the full graph, every vertex has out degree L plus 1. So you have 4 edges from each vertex, and that gives you kind of the full structure of the volcano. If we look at I think on the next slide I have a split case. So this is L equals 2 in this same CM field. In the split case, you get thinking of the surface as a subgraph of the volcano, you get degree 2 for every vertex. So here you see you have 2 edges. And so when we talk about Heegner points, I'll come back to these examples and kind of show you like what are some examples of Heegner points on these graphs. All right, so with that said, we're going to care about Heegner points in this talk. So what is a Heegner point? Well, it's a special type of CM point. So it's a CM point where, okay, it's induced by an isogeny. We're thinking about CM points on x naught of n between two elliptic curves E1 and E2. This is a Heegner point if E1 and E2 have CM by the same order. So if the geometric endomorphism rings of E1 and E2 are isomorphic. Right, so in this case, this is a CM point by the CM order O, but it's one of a special type. And this is what I'm calling a Heegner point. Some folks might say you need some extra conditions in your definition of a Heegner point, so maybe I should assume those throughout this talk as well. In particular, it's common to require that your order O has discriminant relatively prime to your level n. Some folks might call it a mock Heegner point, I believe, if it doesn't have that extra condition. You might also require that all the primes dividing L are split in your CM field. These are just simplifications to make it very clear what the residue field of the point is. And so in particular, talking about residue fields of these points, like why, I guess, like what's an initial motivation for why we would care about Heegner points? Like why are these special CM points of interest? One way I like to think about it is that they give points of kind of especially low degree on these modular curves, where I've put this in scare quotes. What do I mean? I mean that, well, if you take any OCM point, by what we've said before, its residue field over K, let's adjoin the CM field, definitely contains this ring class field. So this is like K adjoin the J invariant of E1 or of E2 here. If it's a Heegner point. And so this is as small as it could be. And when x is a Heegner point, you actually get an equality. And you don't just get equality for x, right? So if you have x is induced by this isogeny phi, you also have a dual isogeny phi dual in the opposite direction. That induces a different point on the modular curve, but with the same residue field. And since E1 and E2 have the same order O, you get the same statement for the point on x naught of n induced by the dual isogeny. Right, so you actually get 2 points of especially low degree on your, or kind of getting equality in this containment on on your modular curve from a Heegner point. And here's kind of the volcanic picture. So if we want that condition that our discriminant is co-prime to our level, then you're staying in the surface of the graph, this like level 0, the top of your volcano. In general, this Heegner condition on the geometric endomorphism rings is just saying that the source and target vertex of your path are at the same level. So certainly it satisfies that if they're both at the surface, and that one might require that in the definition of a Heegner point. If you allow for what I think a lot of folks would call mock Heegner points, you could also have something like this where you have, I guess, what is L is 3 here. So this is a 9 isogeny, right? From the an elliptic curve corresponding to this vertex to an elliptic curve corresponding to this vertex. And so this isogeny will be defined over the ring class field corresponding to this order of this discriminant. Certainly you could also have something in level 2 here to another point in level 2 in purple. And so this is just going to correspond to a point on a higher level modular curve. So what is this? 3 to the, I guess we have 1, 2, 3, 4, 5 edges here. So 3 to the 5th, a point on x naught of 3 to the 5th here. Once you take a Galois equivalence class. In the split case, again, if you want to stay at the surface and have actually these conditions most folks require for the definition of a Heegner point, you can do something like this. Like you could have a single 2 isogeny, L is equal to 2 in this picture, from this vertex to this vertex. That'll be defined over the Hilbert class field of this order. F is equal to 1 here. But you could also take a 4 isogeny by traversing this edge followed by this edge. There's no backtracking there. So this is something you can only do in the split case. And okay, from that, you continue that process. You can do that kind of ad infinitum. You can get a point on x naught of 2 to the a for any power a by just repeatedly traversing these two edges kind of in sequence, one after the other. So you get points on x naught of any power of 2 all defined over the Hilbert class field coming from Heegner points. So this is like a great example of what I mean by points of especially low degree. Those will be degree at most 4, or it'll be exactly 4 in this instance because these two edges are exchanged by complex conjugation. But my picture isn't telling you that. I'm just telling you that. Okay. So I think in the last, I don't know, 7 minutes or so of my talk, I'm gonna, as I promised, give you some more motivation for why we care about Heegner points towards, I think, the aims of the seminar. First, by talking a little bit about the history to give some motivation. So, why do we call these Heegner points? Who is Heegner? I'm sure a lot of you now know about Heegner, but his work was overlooked for quite a while in the mid-1900s. So he was known, or I guess he's now known for his 1952 work, which provided, I would say, a solution to the Gauss class number 1 problem. Some folks might say that it was incomplete or there was some error, but now I guess we might refer to that as the Baker-Stark-Heegner theorem. So this is just determining all the imaginary quadratic fields of class number 1. They have these fundamental discriminants. And why is it all these folks? Well, Heegner gave a proof in 1952 work. He was working on the congruent number problem. And for a variety of reasons, so partly I think because the solution was kind of stated tersely maybe in his work, like it wasn't the main focus, the main thrust of his work, partly because he was using the theory of modular functions, which had kind of fallen out of fashion at the time. It wasn't well known to a lot of mathematicians in the first half of the 1900s. Also because he was referencing work of Weber which was known to have some errors, though I think to my understanding, his work didn't actually use anything that was errored, but maybe some mathematicians assumed that his work was also errored for that reason. For all these reasons, Heegner's work was overlooked until Stark and Birch independently looked back at his work and determined that either it was correct or maybe it was incomplete, but it was very salvageable. And at the very least, his methods were kind of correct and on the right path. This followed Baker giving a proof of a solution to the Gauss class number 1 problem, I think in 66, and also Stark independently giving one in 67 in ways that I think were closer to Heegner's methods. And Heegner's methods here, working with the theory of modular functions, motivated the study of Heegner points. So this is the one picture I could find of Kurt Heegner here. And on the next page, we have a picture of Brian Birch. So Birch was heavily motivated by Heegner's work. So he began performing calculations involving these special points on modular curves. And I say on elliptic curves on this slide. So what do I mean by a Heegner point on elliptic curve? So I mean the following. So let E be an elliptic curve, and suppose you have a finite map like this. So you might call this a modular parameterization. So a surjective map from a modular curve, x naught of n, to your elliptic curve E. So if you have any point upstairs, right, you can of course push it forward to E. So we call a point x on E a Heegner point if it's the image of a Heegner point on x naught of n. Right, so you're just pushing forward Heegner points on your modular curve to get Heegner points on your elliptic curve. And I'll say when Birch was doing computations with Heegner points on elliptic curves, he of course didn't know this, but nowadays we know by work of like Files and Taylor and others that all elliptic curves over Q are modular, so they admit a modular parameterization like this. So you can always do this if you start with an elliptic curve over Q, you can get Heegner points. But okay, Birch was performing these computations with his collaborator Stevens, and their data pointed towards a relation between the order of these points on the elliptic curves, these Heegner points, so whether they were finite order or infinite order, whether they were torsion or not in particular, and the ranks of these elliptic curves. And so in particular, I think something that Birch noted was that if you have, or sorry, that a Heegner point on your elliptic curve has infinite order, it's not torsion, exactly when your elliptic curve has rank 1. So that seems kind of surprising. I don't know, like these, the rank is a very, I don't know, from Birch and Swinnerton Dyer conjecture, which was available at the time, right? This conjecture was a conjecture at the time. You know that the rank is the order vanishing at conjecturally at s equals 1 of your Hasave L function, right? A very analytic gadget. And then on the algebraic side, we have these Heegner points, and there seems like there must be some relation between these two things if it seems like Heegner points are related to ranks. And so, okay, Birch was motivated to figure out what is this relation, and had a lot of correspondence with Benedict Gross. So these correspondences are published in a certain MSRI publications volume. I heavily recommend this volume in general for folks in this seminar interested in Gross Zagier and generalizations thereof. But it's also great to see like the history there. Like some of these letters are really great and contain some funny bits. So for example, Birch and Gross are corresponding, and de Gross says that he's found an amusing method for studying Heegner points on the Jacobian of x naught of n. Right, so when you have a modular parameterization like this to an elliptic curve E, that elliptic curve E, at least up to isogeny, is occurring in the isogeny decomposition of the Jacobian, right? It induces a map from E to the Jacobian. And so this is kind of the vantage that Gross is taking here, talking about Jacobians. And so he's talking about how he's studying Heegner points and getting somewhere, and Birch jokingly says, you seem to be opening so many doors that I'm afraid to push. And he remarks that Dick Gross kind of took this as, I don't know, a challenge or encouragement. And so Gross was kind of gung-ho to figure out this relationship. And there's a later correspondence here where Gross is remarking that he's noticed some really amazing things, and he's finding that there is a relation as long as he can prove some, or complete some analytic computation involving these first derivatives of these L functions. He's saying all I have to do to prove this relation is prove this formula, and he's asking Birch and Stevens for more computational evidence as they're performing computations with Heegner points. They're already conjecturing what would be the Gross-Zagier theorem, and then in December of that year, Gross replies saying, "Well, me and Zagier have got it, and here's what they got." So this is the Gross-Zagier theorem. So let's take an elliptic curve over Q. Nowadays, we know there's an attached modular parameterization, but I guess their day you'd say, suppose you have such a parameterization. I'm calling that capital Phi. And then take a Heegner point upstairs with Cm by K, and take its trace on the elliptic curve. So by that, I mean the following. So you have your Heegner point upstairs. You know that over K, its residue field is what I'm calling K of X here. So that's a certain ring class field. It's the ring class field of the corresponding order. And we're saying take all of the, take that closed point, take all of the geometric points in that comprise that closed point, take the corresponding divisor and push it forward to E. Or in other words, take all those points, push them forward to E, and then take their sum in E, because E is in the abelian variety, you can add points. That's what I mean by the trace here. Then you're getting something on E that is Galois invariant over K. Right, so you're getting a well-defined a point with residue field K on your elliptic curve. And Gross-Zagier is relating the height of that point, the canonical height of that point, to the first derivative of the L function of E over K over the CM field at 1. And okay, here's it's gross detail, that relation. It involves kind of this norm of a Neron differential, or you could also take this to be an attached new form to E. And then, okay, so C, everything is explicit in this theorem. I'm just saying C is an integer. And then U and delta here are just units and discriminant of your CM field. So that's all very explicit. The important bit is that you have that the height of your Heegner point, or this trace here, is a non-zero multiple of this first derivative of your L function. Okay, so on the next slide, I'm restating this theorem, except without the gory detail. And the thing to note is that this means that the height of your point is 0 if and only if the first derivative here vanishes. And height being 0 means that your point is torsion. So you're getting a relation between the order of your point and this first derivative of your L function, which you should be able to connect to ranks. Right, so this provides methods for working explicitly, computationally with Heegner points to get bounds on ranks of elliptic curves. So in particular, I mean, you have work of Kolyvagin, which I think came pretty soon after Gross-Zagier, I'm not sure of the year, that gives bounds from above on the ranks. So if you, I think Kolyvagin works with many Heegner points simultaneously, and finds that this observation that Birch noted, that your this trace point on your elliptic curve is infinite order exactly when your elliptic curve over K has rank exactly 1. And there's also you get some finitude of Shah from that as well. And then I think for folks in this seminar, you're probably also interested in generalizations due to Zhang for more general characters. Sarah, but for this talk, I want to leave you off with this statement, and hopefully that helps you to go off towards whatever generalizations you're looking to pursue. Okay, so I'll stop there for questions.
Yeah, thank you for the wonderful talk. Any questions?
Yeah, actually, this class number 1 imaginary quadratic fields, Stark-Heegner theorem that you have mentioned, and also the name of Baker is also mentioned. So, what is the contribution of Baker in that? Or he also proved the same thing?
Yeah, so Baker and Stark independently proved this, and Heegner, I suppose. I think, like I said, I believe Stark's methods were somewhat similar to Heegner's. They both work in kind of the theory of modular functions. Baker's proof was by different methods. So it was basically by what we now call Baker's method, so like linear forms and logarithms of algebraic numbers.
No, that method. Okay. So his method was different, but he proved the same thing using his ideas. Yes.
Exactly. And they're all like, or I guess Baker and Stark are about like a year apart from one another. So it's kind of interesting, like around the same time, but by pretty different methods.
Okay. Yes. Thank you. Yes.
Yep. Thanks for the question.
Yeah, any more questions, comments? No. If not, let's thank the speaker. Thank you very much. Thank you.
Thanks, Debargha, for sharing. Thanks, Freddy. See you sometime. We'll be using the meeting. Email me the slides.
Yeah, I'll email you the slides. No problem.